All right, let's jump right in. Look, you're in the final stretch for your JE exam, and we know every single second counts. So we sat through a massive 4-hour marathon study session and boiled it all down to just the absolute must-know high-yield stuff. Think of this as your last-minute, rapid-fire guide to lock in those key concepts right before you walk into that exam.
Okay, so here's our game plan. First, we're going to get you in the zone for this final lap. Then, we'll dive straight into the core ideas of fluid mechanics and, you guessed it, structural analysis. After that, a super quick, no-nonsense formula cheat sheet. And we'll wrap it all up with those high-yield topics you absolutely cannot afford to skip.
So, this first part, it's all about being super efficient. We're taking hours and hours of study and squeezing them down into the most critical insights. You know, the stuff that's actually going to stick in your head in the exam hall and hopefully turn directly into points on the board.
You gotta love the confidence from the instructors in the original session. They basically said, hey, all the questions, they come from right here. So let's channel that energy, right? Let's treat these next few concepts like they're guaranteed points just waiting for you on the exam paper.
Okay, first up, fluid mechanics. Now these are your score boosters. Seriously, they're the kind of foundational concepts that show up in questions you can solve pretty quickly. If you can just nail these down, you're already building a solid base for a great score.
So, let's start with the idea of an ideal fluid. Now, yeah, it's a hypothetical thing, a theoretical model, but it's the starting point for so many problems. All you really need to remember are two things. It has zero viscosity and its density is constant. So, it's non-viscous and incompressible. That's it.
Okay, you're going to want to pay close attention right here because honestly, units and conversions are a classic exam trap. For dynamic viscosity, you've got the SI unit, Pascal second, and the CGS unit, which is poise. Just burn this into your brain. 1 poise is 0.1 Pascal seconds. Then for kinematic viscosity, it's meters squared per second versus the Stoke. And the magic number to memorize? 1 Stoke equals 10 to the power of minus 4 meters squared per second. Trust me, knowing these conversions is absolutely essential.
Now, center of buoyancy. It sounds way more complicated than it actually is. It's really simple. It's just the center of gravity of the water that an object displaces. You know, the water it pushes out of the way. And that exact spot, that's where the upward buoyant force pushes from.
So, what's going to happen? It's simple. It sinks. Just picture a little tug-of-war. If the downward pull of its weight is stronger than the upward push from the buoyant force, well, down it goes. This simple balance of forces is everything. It's what decides if something floats, sinks, or just kind of hangs out in the middle.
The original session used a really great analogy for this that's kind of hard to forget. They said, imagine a government that just refuses to change its policies no matter what. That's like steady flow. The properties at any one point don't change over time. But a government that does change its policies, well, that's unsteady flow. It's just a clever, simple way to visualize the difference.
All right, let's switch gears and tackle what can be a core challenge for a lot of people, structural analysis. We're just going to quickly decode the most important things you need to know about beams, stress, and of course, the properties of materials.
This is a really critical distinction to get. So, imagine you heat up a metal bar that's just sitting there, free to expand. What happens? Nothing really. No thermal stress. But what if you constrain it? You know, you fix it at both ends, kind of like a railway track. Now when you heat it up, it has nowhere to go, so this huge compressive stress starts to build up. Understanding free versus constrained is absolutely key for the exam.
Okay, this is a classic mix-up, so let's clear it up right now. Ductility is all about being able to draw something out into a thin wire. Malleability is being able to hammer or roll it into thin sheets. So just think, ductility for wires, malleability for sheets. Got it?
So if a question on Euler's column theory pops up, just remember it's all based on a perfect world, right? The theory assumes the column is perfectly straight, the load is perfectly centered, and the material is totally uniform. Why does this matter? Because these exact assumptions are prime material for multiple choice questions.
The point of contraflexure. The definition is super simple. It's the spot in a beam where the bending moment is exactly 0. That's it. It's the transition point where the beam's curve flips from, say, smiling to frowning. So just remember, contraflexure means 0 bending moment, period.
All right, time for a rapid-fire round. These are the formulas you just gotta know. No negotiation. Let's blast through them really quick.
Okay, remember that constrained expansion we were just talking about? This is the formula for it. The stress, sigma, is just Young's modulus E, times the coefficient of thermal expansion, alpha, times the change in temperature, delta T. E, alpha, delta T.
This one's simple, but it's so important. The stress you get from suddenly dropping a load on something is exactly, and I mean exactly, double the stress you'd get if you applied that same load slowly and gently. Just remember, impact stress is double static stress.
All right, bending stress, or sigma b. You get this by taking the bending moment, m, and dividing it by the section modulus, z. And z is really just a number that tells you how good the beam's shape is at resisting bending. But here's the golden nugget to remember. Bending stress is always zero right down the middle, at the neutral axis.
And finally, let's wrap up with some high-yield data points. We're talking about specific numbers, conversions, and little facts that pop up all the time as standalone questions. Honestly, this is all about pure memorization for some quick and easy points.
So just as a fun little aside, the original marathon session ran a poll to see who was tuning in. Turns out the civil engineering army was out in force, a massive 72%. But hey, it really doesn't matter what your branch is. These concepts are fundamental engineering, and they're vital for absolutely everyone.
Okay, think of this as your quick reference databank. You should definitely memorize these. Like Poisson's ratio for aluminum is 0.33. That's just how much it gets thinner when you stretch it out. And look at the coefficient of discharge for a Venturi meter. It's super high, like 0.98. But the absolute most important takeaway here, Young's modulus is an intrinsic property. That means it belongs to the material itself. It doesn't matter if you have a big piece or a small piece, the value doesn't change.
And there you have it. That's our rapid review. We'll just leave you with this one last thought. It's one thing to memorize that Young's modulus is a constant property, but understanding why? Well, that's what separates just knowing facts from truly understanding the engineering. And that deeper understanding, that's your secret weapon for solving those trippy problems you haven't seen before. Now go ace that exam. Good luck.